Hi, my name is Sherry Ricardis. Today I'm presenting my capstone research focused on the estimation of biological age. The estimation of biological age reflects how old a person seems biologically based on biomarkers compared to their actual chronological age. The goal was to explore which biomarkers and lifestyle factors most strongly influence biological aging and to evaluate whether linear regression models and machine learning models can improve the accuracy of biological age predictions. As people live longer, it's becoming more important to understand how we age and what factors contribute to healthy aging. Biological age refers to how old our body seems based on cellular and molecular changes, which can be different from our actual age. Factors like chronic inflammation, stress, and lifestyle habits, such as diet, sleep, and exercise, can speed up the aging process. By looking at specific biomarkers, we can estimate a person's biological age and identify potential health risks earlier. The goal of this project was to build a predictive model of biological age using data from the National Health and Nutrition Examination Survey, which includes a wide range of biomarker and lifestyle variables. One objective was to identify which indicators are most strongly linked to accelerated aging. The study also compared the performance of different modeling approaches, specifically traditional linear regression versus machine learning models like random forest and bag trees. Finally, the project aimed to support future health strategies by highlighting modifiable factors such as physical activity and inflammation that could slow biological aging. This project used data from the 2001 and 2002 National Health and Nutrition Examination Survey, which includes detailed health information from a nationally representative sample of U.S. adults. Multiple data sets were merged using participant IDs to create a complete file. The final sample included 1,309 adults with both biomarker and lifestyle data. Key variables included telomere length, C-reactive protein, which is an inflammation marker, glucose, insulin, LDL cholesterol, triglycerides, vitamin D, BMI, physical activity, general health, age, and gender. GRIM age, which is a DNA methylation-based clock, served as the biological age estimate because of its strong connection to age-related health risks. The analysis combined exploratory data review, linear regression, and machine learning models, such as random forest and bag trees, to compare performance in predicting biological age. This study focused on three main research questions. The first asked whether specific biomarkers like telomere length, DNA methylation, cholesterol, glucose, and insulin could be used to estimate biological age. The hypotheses tested whether there was a linear relationship between these biomarkers and biological age. The second question explored whether lifestyle factors such as physical activity and fitness added predictive value to beyond of what biomarkers alone could explain. The third question looked at whether the mean difference between biological age and chronological age was greater in individuals with poor health indicators like high inflammation or poor glucose and insulin control. To test these hypotheses, both linear regression and machine learning models, such as random forest and bag trees, were used. GRIM age, a DNA methylation, was used as the main proxy for biological age throughout the study. The literature shows that biological age provides a more accurate picture of how a person is aging compared to chronological age, because it reflects the actual cellular and molecular changes. Telomere length and DNA methylation clocks are two well-established biomarkers, and studies show that combining them leads to better predictions. Researchers have also found that models using standard health data along with machine learning techniques, perform better than traditional methods. When multiple systems are analyzed together, such as inflammation, metabolic health, and immune function, the estimates of biological age become even more reliable. Many studies highlight the potential of using these tools for early detection and to personalize healthcare by tailoring strategies to the individuals based on their biological aging patterns. This project followed a quantitative research design. The dataset includes a wide range of health and demographic information. Biological age was estimated using Grim age, which is the clock used in aging research. For the analysis, multiple linear regression was used first to provide a baseline. Then machine learning models, including random forest and bag trees and support vector machines, were applied to test whether they could improve predictive performance. To evaluate the model's performance metrics like R squared, root mean squared error, and mean absolute error were used to compare accuracy across approaches. The analysis began by handling missing values using mean imputation. Continuous variables were normalized to ensure consistency across features, and categorical variables such as gender and general health were dummy coded. To reduce multicollinearity, feature selection was guided by correlation analysis and variance inflation factor. Since the focus was on explanatory modeling rather than prediction, the data was not split into training and testing sets. Regression analysis was conducted in Python. Also, machine learning models were applied to assess whether they offered improved accuracy. There were several limitations in this study. First, the National Health and Nutrition Examination Survey data is a cross-sectional data set, which means it only provides a snapshot in time. This makes it difficult to analyze how the aging progresses over the long term. Missing biomarker data also reduced the final sample size. Some variables like physical activity and general health were self-reported, which introduces the potential for biases. Finally, where statistical and machine learning models are powerful, they may not fully capture the biological complexity of aging. Even though the data is de-identified, this is the ethical concerns, it's still important to handle it responsibly. In real world research, getting informed consent and being transparent about how data is used are essential. Predictive models, especially in sensitive areas like healthcare, should be applied with care to avoid causing harm or reinforcing bias. And while biological age estimates can offer useful insights, it's important not to overstate their accuracy, especially when they're being used to guide real-life decisions. These findings show that biological age can be estimated using a combination of biomarkers, lifestyle factors, and demographics. The most significant predictors were telomere length, C-reactive protein, vitamin D, age, gender, and self-reported health for linear regression. Linear regression provided some insights, but explained less of the variation. On the other hand, machine learning models, especially random forest and bag trees, achieved higher accuracy. Random forest identified age, BMI, weight, telomere length, and vitamin D as top predictors. Adding lifestyle and inflammation-related variables improved the model's performance beyond biomarkers alone. Overall, the results support using machine learning to improve biological age prediction and guide more personalized health strategies. The dataset included 6,621 records, and the average values provide a general snapshot of the group's overall health. There was a large variability in several biomarkers, especially triglycerides, BMI, and weight. This kind of spread matters because it it can affect how models learn and predict. The summary statistics also helped identify which variables had missing values. For example, C-reactive protein, glucose, and insulin had fewer data points compared to the others. Overall, these insights guided how missing values were handled and helped shape the transformation strategies used during preprocessing. Examining variable relationships helped identify which factors were most relevant to biological aging. Grim age showed a positive linear relationship with chronological age, confirming that biological age generally increases as people get older. Telomere length, C-reactive protein, and vitamin D showed weaker and more scattered patterns in relation to grim age and chronological age. While telomere length appeared to have a slight negative trend, and C-reactive protein a possible positive trend, neither showed a strong or consistent relationship. Vitamin D showed little to no visual correlation. These variables may still be meaningful when combined with the others, but their individual predictive strength appears limited in the scatter plots. To test whether specific biomarkers could estimate biological age, a multiple linear regression was run using telomere length, triglycerides, LDL, glucose, and insulin. The model was statistically significant, but the adjusted R-square was only 7.8%. This suggests that while the model has predictive value, it's relatively weak. Among the biomarkers tested, only the telomere length was a significant predictor. Longer telomeres are associated with lower grim age scores, aligning with the existing research on cellular aging. Triglycerides, LDL, glucose, and insulin were not statistically significant in this model, indicated limited predictive power for those markers on their own. So overall, the null hypothesis was rejected for telomere length, but not for the other biomarkers. This shows the importance of telomere length in estimating biological age and suggests that additional variables may be needed for a stronger predictive model. To address whether lifestyle factors improve prediction, physical activity was added to the original biomarker-only regression model. The updated model remains statistically significant, and the adjusted R-squared increased slightly from 7.8 to 8.9%. This is a small improvement in explanatory power. So physical activity is a significant predictor. So lower levels of physical activity were associated with higher biological age, reinforcing the link between lifestyle and aging. Although the gain in explanatory power was very small, the results suggest that physical activity adds value beyond traditional biomarkers. Based on this, the null hypothesis was rejected for physical activity, showing that lifestyle behaviors can contribute to biological age prediction. This model explored whether individuals with poor health indicators tend to have a larger gap between their biological and chronological age. The regression was statistically significant and explained a substantial portion of the variance in grim age, with an adjusted R-square of 76.4%. Key predictors included chronological age, telomere length, C-reactive protein, vitamin D, gender, and self-reported health status. Higher biological age was associated with older age, higher C-reactive protein levels, and being male. In contrast, longer telomeres, higher vitamin D levels, and better self-rated health were linked to lower biological age. Based on these results, the null hypothesis was rejected for C-reactive protein, vitamin D, and self-rated health, indicated that these variables significantly contribute to biological age estimates. Linear regression served as the baseline model and gave a basic understanding of variable relationships. However, it didn't capture the complexity of the data very well. When we introduced nonlinear models such as random forest and bag trees, the predictive accuracy improved significantly with an R squared value of 84.2%. These models also delivered lower RMSE values than linear regression and the support vector machines. Random forest in particular identified age, BMI, weight, telomere length, and vitamin D as the most important predictors. Overall, the results show that machine learning models are more effective for estimating biological age, especially when dealing with nonlinear relationships between variables. Biological age isn't about how many years we lived. It reflects how our bodies are aging based on biomarkers, lifestyle, and health factors. In this study, telomere length, C-reactive protein, vitamin D, gender, BMI, weight, and self-rated health emerged as key predictors of biological age. While linear regression offered a baseline, machine learning models like random forests and bag trees delivered stronger predictive accuracy by capturing more complex patterns. We also saw that modifiable factors like inflammation and physical activity had an impact on biological age, suggesting that how we live can really affect how we age. These results open the door for more personalized, data-driven approaches to support healthier aging and early intervention. These recommendations build on the study's findings and are meant to guide both future research and real-world use. First, it's worth exploring more advanced models like neural networks and gradient boosting to see if they can improve prediction accuracy beyond what we saw with linear regression and tree-based models. Second, instead of using data from just one point in time, future research should follow people over multiple years. Tracking changes over time would give a clearer picture of how biological aging processes help identify early signs that someone may be aging faster than expected. Third, expanding the range of biomarkers could give us a more complete picture, especially if we include indicators related to oxidative stress, energy metabolism, or DNA repair. Fourth, adding lifestyle and psychosocial variables like sleep, diet, and stress levels could help explain differences in aging that biomarkers alone can't capture. Fifth, there's a real opportunity to turn biological age models into practical tools that people can use to monitor their health and make informed decisions. Finally, we should support public health strategies that encourage behaviors known to slow aging, like physical activity, balanced nutrition, and reducing chronic inflammation. So this concludes my presentation, and thank you for watching.